Okay, maybe we can start. We're very happy to start with Mike Douglas, who will tell us what is string data.
Thanks. Okay, is my screen share up?
It says you've started sharing, but I don't see the slides yet.
How about now?
Yes, they're up.
Good. Okay, so thanks for inviting me, and thanks everybody for coming. It looks like an exciting meeting. So I thought it'd be nice to start by asking this question, and I'll discuss it. The answers I will give will you can actually guess it from the beginning, but I think it's much more to discuss, and I hope that we will continue to discuss this question during the week. So as we all know, the role of computers and machine learning and AI in many fields of human endeavor, and especially science, is only increasing. It's starting to revolutionize some fields, not yet our field, but I think you can argue that the field of protein folding in the computational biology has just been revolutionized by the success of DeepMind's AlphaFold 2. There's certainly much appreciation in the physics and the fundamental physics community of the value of this. There's a whole NSF funded collaboration going on in the Boston Cambridge area, IIFI. It's not just dealing with analyzing experimental and observational data, but there are, as we know, many works that take theoretical problems and in one way or another enhance, find patterns, and the rest. So of course we are here to ask, how can we use this to study string theory? And this is, I believe, the fourth string data conference. So we've been doing this for some time, and I'm not going to try. Of course, this would be the time for the task of a summary talk, but there's many directions that are represented here. To give a few, there's this old idea of automated and assisted discovery of laws and patterns that directly mean something to us as physicists. There's algorithms for better solving the equations, which are central to our field, both the combinatorial sort of equations that come out of construction of string vacua and the numerical equations that come from analyzing quantum field theories and metrics and the like. There's this very old interdisciplinary area of physics, especially statistical physics, bearing on machine learning before it was even called machine learning. I spoke a bit about this at the strings discussion. And obviously, with the whole conference to deal with, I can hardly do justice. And rather than try, I'm going to focus on one, you could say technical, but as we know, very central aspect of machine learning, which is that learning depends on having training data, and the size and the quality of the training data sets is very, very important. Many breakthroughs only became possible once the appropriate training data set became available. So I will try to talk about what can we do to improve the quality of our data, to save our data, that sort of question. Okay, so what is a string theory data set? And we can make a very broad definition. And we have this very famous example, which again, not before machine learning, but certainly before much of the work that people talk about these days, the Kreutzer-Skarka data set that's been extremely valuable over the last 30 years. And of course, there's in principle no difficulty with generating far more data sets. It's much easier than having to build a collider or a telescope or something. You just program your computer and crank it up and maybe get people to run it on their home computers and the rest. But of course, the quality of what one gets that way will be highly variable. And there would be some analogy to trying to have a computer generate mathematics just by making logical deductions. Of course, that's not mathematics. And of course, we have a better sense than that of what string data is interesting. But this reductio ad absurdum certainly shows that it's a thought worth thinking about. What data is important, what's worth saving, how do you save it, how do you distribute it? Okay, so let me just put out a few terms, and a lot of this is kind of specific to these mathematical data sets. So they're not terms that are as much used in machine learning or data data science and the rest. Okay, so the first point I think to make is that we can have a lot of implicit data sets. So there's actually not such a clear line between listing a collection of mathematical objects and just writing the program that generates the mathematical objects. It's true that if you've got the list, you've saved computer time to generate the list, but of course now you're using space to store the list, and it's just a trade-off, which you would probably make for technical reasons. That you have, it's a very long calculation, and you'd like to provide the results, but in fact, most works really don't save the actual list of items they generated. But there is one very essential distinction, which is not always carefully made in certainly papers in our field, which is that a data set is not a list of items. It is a list of items and a probability distribution over them. And so it could be that if you have a finite list, they all are equally probable, but that's a choice, and that's, certainly if you have an infinite list, you can't even make that choice. And so if you're describing your data set, giving a program to generate examples is not necessarily enough. You have to say, well, it's this distribution is uniform, say objects up to size n, and then uniformly sampled. And so I think that's an elementary but important point to make. Okay, there's a term which I kind of like, but there are different words you could use to talk about a Platonic data set, which is one where you've made these choices and really you didn't have to make other arbitrary choices. And so that's one of the great things about the Kreutzer-Skarka data set, is that there's this finite list of reflexive polytopes, and they have them all. And you can say, uniform distribution, and then that's it. It's a very natural object, and that's no doubt one of the reasons why they spent put such effort into generating it and saving it. And not every data set, of course, has that type of property. If you try to make the distribution of finite groups, well, there's an infinite number of finite groups, and it's not totally obvious what distribution to put on them. But there are certainly in between cases where there's not a single natural distribution, but there's a lot of questions that you can ask that within some broad family of distributions, you get roughly the same answer. And so when people, for example, mathematicians talk about the density of prime numbers or numbers that have some property, then of course, it's not like there's some canonical natural measure on the natural numbers, but it's also the case that if you take all the numbers up to some n, you ask for the density within that set, then usually the limit as n goes to infinity is well behaved. And so those are the questions which are universal in that sense, for that ensemble. Okay, so these are again not issues that would come up in the discussion of data science, but as we are interested in really mathematically precisely defined data sets, they are worth keeping in mind for us. And then of course a third point, which I won't really get into detail, but equally important, of course, is well, now how do we distribute our data set? Is it maintained? Is it and in what way is it verified. Okay, this is a point I will come back to. What computational platform supports it and the rest. Okay, so a variety of questions that one could discuss, and it's always good to look back at the previous relevant work. And in string theory, after the Kreutzer-Skarka, there's not that much which is very well known or famous. There's lots of individual data sets from sets of a few papers by one group typically. And of course, fields that have been around longer have much more data collection and generation. And so group theory is obviously a subject of great importance to us, that mathematicians, computational group theorists have existed for a while. And so that should be, you would think, a good source of ideas, of best practices and the rest. And then there are things you can look at, where classification is more central. Groups classification is interesting, but it's usually a question of identifying the particular group you're interested in and its representations and that sort of thing. Whereas a subject like knot theory, you might be more interested in the specific classification. Okay, so I looked around a bit, and what was I looking for? Okay, well, I mean, again, what are the questions that people ask when they set up these data sets? Is there a good data set for group theory that's got all the common examples? For us, in string theory, you might say, well, you really should have, the exceptional examples, and of course, the most famous exceptional ones are for finite group theory are the sporadic simple groups. You can ask how easy is it to use. You can ask how well it works with your software. And for machine learning, the standard really is Python and TensorFlow and PyTorch, and the other main packages are in Python. So it should be usable for that from that. Okay, so what did I learn by looking around? Okay, so by far the easiest thing you can do is look at the big computer algebra platforms, Mathematica and SageMath, and they're maintained. They're not just going to disappear or become not run on your system after a few years. SageMath is open source. That's some advantage. Mathematica has a sizable company that maintains it. They both have good group theory packages. Mathematica has this, it basically represents things. There are many other, user-written packages, but the thing which, Wolfram gives you is based on representing groups as subgroups of permutation groups. And then SageMath, there's this longstanding project of computational group theory called a GAP, Groups, Algorithms, and Programming, developed by a team of mathematicians over the years. And SageMath, being open source, is in a sense able to absorb a lot of these other open source projects and at least provide interfaces. And they're there in the distribution. And GAP is actually quite good, and it has an interface in particular to kind of the defining data set in this field, which is called the Atlas of Finite Group Representations, which also has the sporadic groups, has a lot of group representations. So it's got more than Mathematica. Doesn't have the monster group representation, but if you know how large that is, it's not that surprising. And then these are kind of the easy things to talk about, because now, of course, they only scratched the surface, but now it's really not that easy to explore the rest of this software literature. There are lists that just have thousands of entries provided by various things, not thousands in group theory, but my guess is hundreds in group theory. Okay, so definitely there's something there. Definitely there are things to learn. It's not like there's some sort of clear best practices that we can just adopt. And again, there's quite a bit that one can do. And in fact, there's more. If I pick, for example, interactive theorem verification, which I'll come back to, there's actually a better story in that field, but we don't use that as much. So I talked about group theory. Okay, so there's something to do, and we can't just do what some other community does. But I think it is, again, worth discussing and spending time on this question, which is, in some ways, again, serving the needs of our bigger projects, but still worth discussing. Okay, so I'm going to try to go a little quickly, although we started a few minutes late, I believe. You can tell me how many minutes I have, but I'm going to briefly talk about, again, as mathematical data sets, but even in ordinary statistics, one very central role is played by approximate distributions, like the normal distribution that you spend a good amount of time discussing in a statistics course. And then they have many roles. As physicists, of course, we know that approximations help us think, approximations help us shape a problem. Even if we're collecting data, if we know that it's sort of normal, that makes a big difference compared to something with the heavy tails or some other approximate distribution. And then in math, this has a long history of trying to characterize the interesting distributions by approximations or bounds. An interesting one, which I discovered in research for this talk, is this middle one, Pybur's theorem. So there is an actual upper bound on the number of distinct and non-isomorphic finite groups as a of order up to n. And I should say not of, but up to order n. And it's this power law, n to the 2/27 mu of n squared, where mu is the highest power with which a prime divides n. So again, these sorts of results are actually worth knowing. Okay, so now what I'm going to get into a bit is say something about approximate distributions of a string vacuum. I've reviewed, I'm not going to go through it, but this kind of standard approach to string compactification, which much of our work is built on. And so then there are these interesting results. So this paper of statistics of vacua that I wrote in 2003, this was really the point, that these approximate distributions of string vacua might be simple enough to get. They're certainly simple enough to talk about, and they have value. And again, this work on flux vacua at that time, looking back, I would say one of the main things that I think we learned is that a priori you could wonder, is the cosmological constant in an anthropic scenario where it can take many possible values, but is it distributed out to the supersymmetry breaking scale, or is it distributed out to some higher scale? And it makes a big difference for the relation between the anthropic mechanisms and supersymmetry. And of course, you think about it a bit, and then we made precise that because the supergravity expression has this minus 3w squared term, which is not breaking supersymmetry, it's set by the higher dimensional scale, whatever the flux scale or the KK scale. And so just because you have the anthropic solution does not mean that you favor low energy supersymmetry, which if you had not had this relation, it would have. And so in my thinking, again, this was one of the reasons I was quite ready, and some people were quite ready to say, well, string theory does not really predict supersymmetry at LHC. There's some sort of preference, but it's too weak to claim that there's any prediction. Okay, so then another very even simpler idea, but again one which we use and we should keep in mind, is this idea that there are different observables which we don't know, but at some level of evidence you could argue are independent. So is matching the standard model independent of getting a realistic inflaton inflation? And of course, it's easy to say it, but within this framework, you can give arguments either way. It's not like we know it's the case, but it's very clear how you would check whether that's the case in principle, if you can study large classes of vacua and get these statistical estimates. And then here's a few subsequent highlights of I would say the same general order of importance. That discrete symmetries are disfavored, that the difficulty of achieving the standard model matter content is not so difficult compared to the anthropic tunings, that if you say that, say, cosmological constant is anthropically tuned, that this one you could debate, but I think there's reasonable evidence that the kind of high scale supersymmetry breaking that some of the early works, such as some of my early work, suggested is actually disfavored. This idea that the biggest and most complicated F-theory manifolds have these ridiculously large number of vacua has shaped a lot of recent work. And I'll mention, problems where, they're clearly important and we don't know as much. So one of the questions which is in that original paper, which I really would like to see progress, is to show duality on a statistical level, that you've got two constructions that claim to be the same set of vacua and that the statistics really should be the same. And then find a way to get a representative set, any kind of argument that a given set of vacua actually is representative of some large known set, or hopefully, someday the whole set of string theory vacua. So that's all we ultimately need to be able to make well-founded statistical statements about real string theory. Okay. So can we use machine learning to learn these really arbitrarily complicated distributions with all the structure of string theory? And the answer is clearly yes. There will be many talks about such questions and attempts in the conference here. And there's this larger area that this naturally sits in. We would say it sits in string theory of physics, but I think it's at least or more related to the area of generation of mathematical conjectures, and in particular, again, many more works, the works I've just talked about, more works. This recent Nature article of the DeepMind group, Davies et al., is, I think, very clearly will get a lot of attention, and not a turning point necessarily, but an important benchmark or point to notice in this direction. And now I want to talk a bit about questions like, 5 minutes? Yeah, I want to talk a bit about questions like, how do we judge claims that come out of this work? How do we reproduce and build on this type of work? Okay, so this question of how do you judge works where there's reasoning, but it's a computer program and it's too much for any person to, or even a group of people to go through. And of course, this problem existed since the beginning of computation, but it really came to the fore with the proof of the four-color theorem, the original 1976 one. And it's because there's a difference between doing lots of calculations and then fitting them into some larger picture, which is also supported by theory and analysis, and claiming that, here's a theorem which we've proven, but it's got these, thousands of computer verifications. And so how did people, because mathematicians definitely accept this proof now, and the main ingredients of that were independent reproducing the somewhat simplified version of the proof, and then a formal verification of the proof that really was translated into a purely logical terms that could be verified. This is another technology I've spoken about elsewhere that's going to become more and more important. So machine learning, one has all these issues and interpretability. As you know, these models can be very difficult to interpret, and one has to somehow simplify a model with millions of parameters. One has to guard against mistakes like doing an interpolation and then using it for an extrapolation, which is a standard thing one can do. And so there really is this issue: how do we know? How do we validate? How do we convince people that our machine learning results are right? And I think ultimately the answer has to be that machine learning generates conjectures, and the claims have to have some sort of proofs. Okay, I just don't think there is any lesser standard that's meaningful, but it doesn't necessarily mean rigorous proof. Obviously, mathematicians will insist on that, but what do physicists insist on? And I think this is an important question for us to discuss. And I'm not sure. Here are some ideas. If you don't just study the case which is needed for your physical prediction, you formulate a claim in some generality, so you can get more tests. You can test on exactly solvable examples. So I think that's going to be an important practice movement going forward. Another one I'll say again, don't accept uncontrolled extrapolations, so if you train on examples of, some difficulty or dimension up to 20, then you really can't claim it works for much bigger numbers unless you specifically look at that point and say, well, yes, here's an argument that the asymptotics as n grows, my client has the right asymptotics. You should at least do that and ideally give much better arguments. Okay, and so then the second point of reproducibility and extensibility, again, a lot of difficulties in machine learning already, and especially because the resources to get the best results are not widely distributed. And so we really do, again, if it's mathematical proof, in principle, that can be checked, but there's a real danger of, powerful results coming out that being asked to accept on faith. And so, again, this is something that, medical research one might think about more, but we have to think about it too. And another point in this direction of reproducibility I would make is it really strikes me that the machine learning world and the computer science world has this great advantage that they have these large standard platforms where they're very used to, and we've all done it, use complicated systems, which other researchers developed in a kind of a plug and play way. And I think the rest of the scientific world has a fair amount of catching up to do. And that's obviously, machine learning has many advantages, but even this sort of basic kind of advantage of being able to distribute programs and use them is something that we can learn from. Okay, so I'll conclude by answering my question. There's this trivial answer. String data is what the string theorists generated in writing their papers and doing their work. But the non-trivial part of that answer is then to validate and save the worthwhile data sets that we generate in our work, and to also really do some of that work to better automate the parts of the problem we understand. As I began, by describing, even the situation for areas like group theory is not, in my opinion, totally satisfactory. And I do think that this project is going to happen on a, it's starting to happen, that 10 years from now, we will have papers which really do have the data, the notebooks or the computer generated summaries as all part of it. And then that way our research lives will be different and better. And, I think physicists should try to, not just contribute, but be in the forefront of these developments. So let me thank you for your attention and ask for questions.
Thank you. Any questions? Eva?
Sorry, did you say me?
Yes.
Yes. Okay. Thanks for the very interesting talk, Mike. There is a subject that involves group theory and geometry and string theory, which is has some famous data sets involving hyperbolic geometries. So I think the most famous data set there is in 3 dimensions, but for us, we need in principle arbitrarily high dimensions, but let's say 6 or 7. And that's a place where there are proofs of very interesting statements in math about the existence of finite covers that have certain properties that basically boil down to group theory. It's also related to the point about supersymmetry breaking, because almost every manifold is more curved than a Calabi-Yau, and that's one of the early reasons we thought that supersymmetry was far from inevitable at the LHC. So I think that arena is a very fruitful one to continue to work, and it would interface with the mathematical side that, as you say, is particularly well developed. So I wondered if you had any comments on all of that.
No, I mean, I think those are very interesting and good works, and again, another area where these data sets have been developed and have been influential. So thanks for adding that.
Jim?
Hi, Mike. Wonderful talk. I was wondering if you might be able to elaborate on something you got. You mentioned briefly in your talk about statistical independence of observables. 2 of the observables we care about most are the cosmological constant and the standard model. And I know this is something you've thought about a lot. And of course, the extent to which various observables we care about are independent or not is really important from the point of view of these studies. And I was wondering if you might be able to elaborate.
Yeah, I would. That's why, I mean, there are lots where I would not take such a strong view, but I would certainly take the point of view that the cosmological constant is independent of almost everything else for the simple reason that it gets these additive contributions from every sector of the theory. So any theory that has any kind of hidden structure, it doesn't even have to be matter, but these fluxes, with any combinatorial possibilities, it just seems guaranteed to me that those choices will come in to make this effectively independent. Yes.
Just because everything is contributing in a sense.
Yes, that's right. I mean, again, there are many, and because it contributes with both sides, so like, if you make the similar argument for the supersymmetry breaking scale, because everything contributes with a plus sign, that's different. But once everything contributes with both signs, and there are many contributions with sizable ranges, as we said, the fluxes are controlled by these internal scales, then I think that's already a strong argument.
Wonderful, thanks.
Okay, anyone else? Well, if not, let's thank Mike. And the next speaker is Yang-Hui He, who will tell us about the world in the grain of sand. Yang,